My teacher is putting the stuff on YouTube to show off a little bit. I know you're not watching. Anyway. Save it. Okay, so we left off last time talking about these things. What are the properties of membrane? You went over this morning a little bit, and then we talked about that if there is an unsaturated fatty acid, that cell membrane is more porous, if you would. And then we talked about 6 major functions of membrane proteins, and you saw a video. I talked about HIV, and then we talked about membrane built by endoplasmic reticulum and Golgi apparatus. I talked about that, and I believe this is where we stopped. I think that's where we stopped a little bit, but let's go over it. Might as well. So let's go over these quickly. What is permeability of the lipid bilayer? Again, lipid bilayer, there are 2 layers of hydrophobic non-polar molecules, such as hydrocarbons, can dissolve in the lipid bilayer and pass through the membrane. Okay, pass through the membrane, and rapidly hydrophilic molecules, including ions and polar molecules, do not cross the membrane easily. What are the transport proteins? I think I talked about this last time too. Transport protein allows passage of hydrophilic substances across the membrane. Channel proteins like aquaproteins, so the water molecules that we're talking about in here, that they get inside of the cell, they go through aquaprotein. They are protein molecules, channels that water molecules can pass through them. Other transport proteins called carrier proteins bind to molecules and change shape and shuttle them across membrane. A transport protein is specific for substances that is involved. What is passive transport? Okay, is diffusion of substances across a membrane with no energy investment. So when molecules, some molecules, I'm not talking about all molecules, when some molecules go across membrane, there is no energy, there is no ATP needed. ATP in your cells, that's what we all strive for, ATP. We all work hard for ATP, because ATP inside of your body, inside of your cells, act like money. You have money, you have things. You have ATP, you have energy to do things. Am I making some sense? So inside of your body, ATP is like money. It's a source of energy for us. ATP becomes ADP, and then of course we can do activities. Right now I'm doing this. I'm breaking ATP to ADP. Okay. So anyhow, I'm saying that for passive transport, there is no ATP needed. Like aquaporin molecules. When this is aquaporin, water molecules coming in, no ATP needed. And you will see soon other molecules, he talked about it, sodium potassium pump, ATP is needed. 3 sodium goes outside of the cell, and 2 potassium comes inside of the cell, 1 ATP spent. Okay, and you will see that. So not always everything is free. This is free, no ATP needed. Okay, as diffusion, the definition of diffusion, I might be different than your textbook, but you must go with my definition. Diffusion is movement of molecules, any molecule. I'm not saying water, I'm not saying gas, I'm saying any molecule. Movement of molecules from high concentration to low concentration is called diffusion. Okay. Although each molecule moves randomly, diffusion of a population of molecules may be directional. Usually it is directional. Molecules, in case of diffusion, you saw it in here, the examples I had here, they move from high concentration to low concentration. Here it is, molecules of a dye, we talked about this. They move from, here is a high concentration of the molecule, this is diffusion. they go to a lower concentration, and finally when equilibrium is reached. If I grab sugar and put it in a container, right? Put it in a beaker or put it in your coffee mug. If I grab some sugar in here, what are the ways that I can speed up the dissolvement of sugar in that water? Stir it. Heat it up. If I do not want to heat it up, if I do not stir it, I let it sit for long time. All of that sugar molecules dissolve equally in that water for a long time. Okay, that's what equilibrium means. Okay, so diffusion of molecules, diffusion of two molecules, eventually you have reached an equilibrium across the membrane. Of course, this is a membrane. I call it, I would not like to say use the term diffusion across a membrane. That would be, this would be a movement of the solute. This would be the movement of solute across the membrane until it reaches equilibrium. Animation, let's see what this animation has to say. A lot of times these animations have good information.
The plasma membrane is selectively permeable. It lets some substances through and not others. The hydrophobic interior of the bilayer is one reason membranes are selectively permeable. Hydrophobic molecules, those that are soluble in lipids, can easily pass through the membrane. In addition, small molecules like O2 can sneak between the phospholipids of the membrane. On the other hand, large hydrophilic molecules like glucose and ions, such as sodium ions and hydrogen ions, cannot pass through the membrane unaided.
Yes, so not everything can pass through the membrane. What is passive transport? I think I talked about that. Substances diffuse down their concentration gradient. Okay, let's talk about that. What is concentration gradient? Right here, the concentration gradient of this molecule, alpha, salt, whatever you say, sugar, is higher outside of the cell than inside of the cell. That's what concentration gradient means. Concentration gradient means when substances, not water, I'm not talking about water, the solute, you know what solute means, is higher somewhere. In this case, concentration gradient is higher inside of the cell than outside of the cell. Let's see what it says. Substances diffuse down their concentration gradient. Substances diffuse. If this molecule is supposed to diffuse right here, the alpha molecules, and they could pass through the membrane, which way the molecules would move? From outside to inside of the cell or from inside to outside of the cell, based on the definition you have on the board.
Outside to inside.
Very good. You have more of it outside. The cell, the membrane, wants to be in equilibrium. So the molecules move, this alpha molecule, I'm not talking about water molecules, this substances, this solute, if you would move from here to there. How about here? What would be the scenario here? You have more concentration gradient inside of the cell than outside of the cell. What would happen if these molecules could move in and out? Where the molecules would move? From inside to outside. The molecules, the solute, would move from outside to inside, region which the density of chemical substances increase or decrease. No work needed must be done to move substances down the concentration gradient. Of course, we're talking about passive transport. When the solutes are moving from outside of the cell to inside of the cell, no ATP needed. When these molecules are moving from inside of the cell to outside of the cell, these solutes, I'm not talking about water, I kept repeating that, no ATP needed. The diffusion of substances across a biological membrane is passive transport because no energy expended, and then we already talked about that. Osmosis, effect of water molecules. Definition of osmosis is, this is the best definition you're going to get for osmosis anywhere else, movement of water molecules from high concentration to low concentration through a selective permeable membrane. Through a selective permeable membrane. Okay, water diffuses across a membrane from region of lower solute. He's talking about that. It's good that he's giving you same definition. But I talked about water. He's talking about solute, the concentration of solute. Region of lower solute concentration to region of a higher solute concentration until the solute concentration is in equilibrium on both sides. Okay, so diffusion, water when water molecules diffuses. Here is an example. He has for you the water molecules are moving. When water molecules move from this side of the tube to that side, now this is there is more water on this side. They were equal sides at the beginning of the experiment. At the beginning of the experiment, they're equal, but now, after a while, after 10, 15 minutes, half an hour, which you did on use the last time, whenever it was. Okay, so the water molecules went, of course, from that side to that side. Okay, here on this diagram, at the beginning of the time, where is more solute? Side A or side B? A, B. Huh? Which one does have more solute? A. A has more solute. A has more solute. Okay, so water molecules move, and when water molecules move, they move up here. And same as selectively permeable membrane osmosis, water molecules, they're showing you the same thing here. The water molecules are moving in and out. Okay. Water balance of cell without cell wall. Tenacity is the ability of surrounding solutions to cause a cell to gain or lose water. That would be the tenacity of a cell. Isotonic environment, that is when you have concentration of solute inside and outside of the cell is same. That's what they call it iso. On your prefixes, suffixes, iso means what? Same. Okay. In hypertonic solution, that is, I wrote it down here, when you place the cell in hypertonic solution, an example of that would be sea salt. The water from the ocean, you're not supposed to drink it. That's hypertonic environment. Okay, and hypotonic environment is deionized water. I do not drink deionized water. It does not have any minerals. Some people do. They go buy it and they drink it. I don't know why they do that, but I guess that's healthy. I don't know. I'm not condemning it because I don't know anything about it, and I'm not for it either. But anyhow, here it is. What happens? I didn't draw it for you guys. What happens to a cell when you place a cell in a normal solution? Why is lysine? Oh, you put it in hypotonic. You place the cell in hypotonic environment. Is that right? You place the cell in hypotonic environment. Inside of the cell, these are red blood cells. We used to do this lab long time ago, but because of hepatitis and HIV, we don't do it anymore. Even with sheep blood, we used to do it with sheep blood. Get sheep blood and put it in a salt solution, and then you would see the cells would last. In normal tap water, if you place a red blood cell in tap water, nothing will happen to it. If you place a cell in hypertonic environment in salt solution, the cell will shrivel, shrink. Why? I hope you understand why. When all of the water molecules here leave the cell, what will happen to the cell? The cell shrink. That's what's supposed to happen to your dialysis bag on last time. I don't know what happened. Maybe we should repeat that experiment, and you get it right this time. But you know what is supposed to happen. Here, when all of the water molecules move inside of the cell bursts. The cell explode, burst. So a lot of water molecules chunk are going inside of the cell. And then of course you have this for plant cells. They have a membrane around them. They become flaccid in isotonic environment, and they are normal in hypotonic environment. And of course they are plasmolized in salt solution. You give them salt solution, they will die. And then you give them isotonic, you give them deionized water, they become flaccid. Okay, and then of course you give them the normal well water, then they will be normal. Here is a video, something you did not do on Tuesday. Maybe you did. Brian tried to do this. Here is you see the chloroplasts are moving around. It's called cytoplasmic streaming inside of the cell. Right here, they're moving. And then when you add salt solution to this, I'm assuming they add salt solution to this. Now look, they're shrinking. The cell wall is remaining the same, but this is shrinking. The cell is shrinking. Right there. Now this is the cell. Right here. This is the cell with all of the chloroplasts inside. Of course, it will die. Do you guys see that? This is something Brian have done for you on last time, whenever it was. He took a microscope, he took Eladia leaf, and then he adds salt solution for it. Okay, shall we go? Here is a target environment. Here is a chloroplast moving inside of the cell. Elodia is the name of the leaf, the plant. And what happened here, the cell kind of got busted. Now you don't see the normal pattern of cytoplasmic streaming. Of course, the microscope is going out of focus as well. He's trying to focus it. Okay. Water balance of cell with cell walls. Cell walls help maintain water balance. A plant cell in a hypotonic solution swells until the wall opposes uptake. The cell will now be turgid firm, as you saw it on the video. If a plant cell and its surrounding are isotonic, there is no net movement of water into cell. The cell becomes flaccid, becomes limp. Okay, and then the membrane pulls away from the cell wall, causing the plant to wilt, and a usually lethal effect of plasmalosis. It's called, when you add salt solution, which you've done this, that would be the case of salt solution. Okay, what is facilitated diffusion? Passive transport aided by protein. In facilitated diffusion, the transport proteins include channels proteins and carrier proteins. Aquaporin facilitated the diffusion of water. You are familiar with aquaprotein. I talked about it. The channels on these are little channels, aquaprotein, right here on the cells. They facilitate right here. They're all over. They facilitate movement of H2O inside of the cell or outside of the cell, as a matter of fact. It depends where there is more concentration of water. So that would be aquaprotein. Ion channels facilitate the diffusion of ions. Some ions channels called gated channels open or close in response to stimulus. So ion channels, maybe I should draw something different. Ion channels, by far there are less of them. This is ion channel, ion channel, ion channel. For example, this would be for sodium, this would be for calcium. They're different. The ion channels that allows ion in does not allow calcium in. Calcium channel is different. I draw that as a rectangular. I draw this sodium channel as a oval shape. I hope I'm making some sense. So they are different. Ion channels for each ion, the protein shape is different. Okay, extracellular fluid are coming inside of the cell. That's a protein molecule. through a channel protein, and then changing shape of proteins. This molecule does not change its shape, but that molecule, that protein molecule in phospholipid bilayer, they change their shape. These protein molecules, these molecules, whatever it is, let's say calcium, is coming in, the protein molecule have to change the shape. Okay, just like enzymes, which we will talk about them later on a little bit. Okay, what is active transport now? Everything that I talked about so far, all of these PowerPoints, all of those PowerPoints were passive transport. It means ATP is not needed. Active transport, that is when ATP is needed. What is active transport? Uses energy to move solutes against their concentration gradients. So, active transport in most cases, you have this, you want to move this molecule, that one, opposite of the way it's supposed to be moving. See, these alpha molecules are moving inside of the cell, right? To reach equilibrium. Am I making some sense? But when we're talking about active transport against their concentration gradient, for doing that, you need a pump. They call them a pump. But these pumps need ATP because you're moving the molecules opposite of their concentration gradient. I hope I'm making some sense. Okay, that's what happens. Facilitated diffusion is still passive because the solute moves down its concentration gradient and the transport requires no energy. Active transport protein, however, can move solutes against their concentration gradient. Active transport usually uses ATP, as I talked about it. Specific protein embedded in a membrane. Here is a sodium-potassium pump that I asked last time what it is. Active transport allows cells to maintain concentration gradients that differ from the surroundings. The sodium-potassium pump is one type of active transport, and 2 potassium in and 3 sodium outside of the cell. Right here, you have inside of the cell, outside of the cell. What happens? 3 sodium goes outside of the cell, and 2 potassium comes inside of the cell at the expense of 1 ATP. And all of these are protein molecules. Don't not worry about A, B, and all of that. These are all protein. What are these guys? Oh well, it says oligosaccharide. Steven, am I making some sense? Yeah, some sense. If you have read your notes last night, or you've done what I asked you, the homework, whatever I say here should make sense. Should make sense. If not, you read the textbook, you did your homework, you did the lab report. Everything I say here should make sense. If not, yes, 4 days off. Enjoyed it. I watched 2 movies during that 4 days off. One movie that you all should watch, I think. It's Inside Out. Is that right? Have you seen the cartoon? Yes. And then the other movie I saw, Martian. It's okay. It would be nicer if Arnold Schwarzenegger would play. I'll be back. Tell them. Have you seen that movie, Martian? Maya, have you seen that movie, Martian? But you should see Inside Out. Have you seen it? You've seen Inside Out? As I said, I didn't read my notes. I watched 2 movies. I had 4 days off, 2 movies. Okay, so passive transport is when molecules are moving inside of the cell from high concentration to low concentration, usually. Okay, this is facilitated diffusion. This is diffusion, moving molecules, right? Not through the protein molecules. This is a nice diagram, I think. This is diffusion. He's talking about diffusion And then he's talking about facilitated diffusion, no ATP needed. Molecules moving through the protein molecules. However, this is active transport. Active transport is moving molecules, and while the molecules are being moved, of course, ATP is needed for active transport. Membrane potential is the voltage difference across a membrane. Voltage is created by differences in the distribution of passive and negative ions. Maybe I should draw this quickly because when you go to physiology or other classes, you do need this. I'm going to erase this. What am I saying there? What is being said there? Right here, you have a cell membrane, right? You all know what I'm talking about. Inside of the cell, you have some protein, you have ATP. These are all negatively charged. Negative. You all know what I mean by negatively charged. And outside, you have a lot of sodium. And sodium, as you know, it is positive charge. So I'm going to draw positive, positive, positive. So inside of the cell, and outside of the cell. Inside of the cell is negatively charged, outside of the cell is positively charged. If I attach this to a voltmeter, there is an L here. Okay, and then I put one electrode outside and one electrode inside of the cell. Oh, and turn on the voltmeter. The voltmeter is going to read, for example, minus 70 millivolt. That's what polarity means. That's what that means. It means inside of the cell is negatively charged and outside of the cell is positively charged. How strong of a negative inside of the cell is? Minus 70 millivolt. Okay, and then when you stimulate the cell, you poke a cell, what happens? All of these cells, all of the sodium rushes in, and then inside of the cell becomes, even though these guys do not get out, inside of the cell becomes more positive charge to 40 plus 40 millivolt. That's what that means. Membrane potential. It means there is polarity across membrane. Okay, here it is. Hydrogen ions are being pumped out. And the best example is your stomach. The cells in your stomach have hydrogen pump, proton pump, and then of course at the expense of ATP, extracellular and cytoplasm. Here is sugar molecules. When sucrose is moving inside of the cell, of course, sodium is diffusing inside. There's a lot of this. I'm not going to get into too much of it. When sodium is moving against its gradient, right? In this scenario, in a best worst situation scenario, the hydrogen ions, I said sodium, I'm sorry about that. Hydrogen ions supposed to go that way, right? From high concentration to low concentration. That's what it's supposed to happen. But when the hydrogen ions are being pumped against their gradient, against their concentration gradient, then ATP is needed. I hope I emphasized that enough today so you know what I'm talking about. Wow, there's a lot of information here. Yeah, it's good information. Okay, let's talk about it. Bulk transport across the plasma membrane occurs by exocytosis and endocytosis. Before, maybe I should forget all of this for now, but tell me what does exo means what? Exo means what? Exit, right? Getting out. Cyto means what? Cell, getting out of the cell. And what is endo means? Coming inside of the cell. And cyte, it means cell. Getting out and getting in a bulge. Huge bulks, okay? So let's go over what are they. Small molecules and water enter or leave the cell through a lipid bilayer via transport protein molecules, blah, blah, blah. We already studied that. large molecules such as polysaccharides and proteins across membrane in bulk via vesicles. Okay, and we already talked about vesicles in here. For example, I did show you these little gray, this is a contractile vacuole, but these little gray, these are vesicles, right? So what we are saying that molecules can get in and get outside of the cell by vesicles. Bulk transport required energy. All of these bulk transports, they need ATP. Exocytosis, when the material leave the cell, and endocytosis, when the material coming inside of the cell. Endocytosis happens in 3 ways. Okay, when molecules are coming inside of the cell. When molecules are big, large molecules are coming inside of the cell, there are 3 ways. Okay, let's go over it. Phagocytosis, it means cell eating. Phago, it means eating. Phagocytosis, cell eating. Formation of vacuoles and fusion of vacuoles with lysosome. In this model, in main campus, we have a model that an amoeba is eating. Imagine my fist is a bacterium that they wrap around their pseudopod. They wrap around this pseudopod around my fist and they eat it. That is called phagocytosis. And I said, imagine my fist is a bacterium. They wrap it around my fist and they eat it. That is phagocytosis. They eat bacteria. And then that is called phagocytosis. It happens inside of your cells as well. But anyway, pinocytosis is cell drinking. Okay, that was phagocytosis when all of a sudden you have a lot of fluid going inside of the cell by formation of vesicles. That is pinocytosis. And then receptor-mediated endocytosis, it means the cell must have a receptor, a protein molecule as a receptor in order to engulf my finger. It must have a receptor. And we already talked about receptor in here. It's a protein molecule. Receptors are protein molecules. They receive. That's what they call them, receptor. They receive. So they match, like HIV. I gave you an example of that a long time ago. If you read your notes every day, then you would know what I'm talking about today. When I say receptor, the first thing should come to your mind is HIV. I showed you the PowerPoint, and you saw it, how the protein molecules of HIV matches our white blood cells receptors, just like that, and that's why HIV gain access inside of our cells. But our liver cells do not have this, they have this. The HIV goes to liver cells, nothing happens. They do not go inside of the cell. I talked about receptors. They call it receptor-mediated endocytosis, getting inside of the cell. Here they are, a few of them. Phagocytosis, a picture of it. A vesicle, a cell membrane is formed around it. And of course goes inside of the cell, and the cell will diffuse with lysosome and breaks this up. Okay. Pinocytosis, when you have a lot of fluid, in that fluid, of course, you have some ions, something, and then a cell membrane is formed around it, and then it goes. What did I write down? Molecules dissolved in droplets are taken up when extracellular fluid is galloped into tiny vesicles. Yes. And then receptor-mediated, these are the receptors, the Y shape are receptors. When these are attached, this triangular attached to them, then they form a vesicle, and then the vesicle goes inside it. That's a receptor-mediated endocytosis. What is receptor-mediated endocytosis? In receptor-mediated endocytosis, binding of a ligand. This, the triangulars are ligand. The triangulars are referred to as ligand. Okay? When ligand attaches, ligand to receptor triggers vesicle formation. A ligand is any molecule that binds specifically to a receptor site of another molecule. Okay? Here is a transmission electron picture of receptor-mediated, how the vesicle is formed, and then this is the beginning of it. And of course, they're showing you this, that is happening. Here is a code. Let's go to chapter 11. I'm done with chapter 7. You guys want a 5 minutes break, restroom break, or you want to move on? Let's take a 5 minutes. You look like you lost a battle. Thank God.